Okay, so I know I lied to you. I lied. I said that in this video we would talk about translation, but we still haven't really finished the actual replication portion yet. And not just replication, but I want to talk about really DNA separation. And we said that DNA separates through a thing called a helicase, which is a protein that uses ATP in order to do its job. But we can separate DNA fairly easily in the laboratory, and that's a lot of times what we need to focus on. You know, how can we do these things in the lab itself? And this is very simple. What you do is that you heat it up. That's it. You just heat it up. And when you heat it up, this is enough energy to basically get that hydrogen bond glue to loosen up and to separate for you so these two strands do not stay attached together. And heat is all that you need. So in a laboratory, it's very easy for me to take DNA, extract DNA, get clean DNA, and then use that DNA and heat it up to a temperature and have these two strands separate from each other. They're called random coils when I do that. So these things fall apart, and they fall apart, and they're still kind of corkscrewy shape or curl shape, but they're called random coils for that reason. But my two strands have at least been separated, and as long as I keep the heat on it, these two strands typically do not come back together. So that is a way that I can separate DNA. Very easily done in a laboratory. You just put some heat onto the thing and it begins to separate and fall apart. Uh, what we see happen though is that we can play off some of our instrumentation because that's what we're all about here, right? It's about instrumentation and how we can measure these things and what can we use in a research environment. So with the DNA, you're going to look at the bases. And the bases are rings and they're aromatics. And these aromatic rings are basically uh, very good components to analyze in a UV vis spectrometer, because we said anytime we have a conjugated system or anytime that we see aromaticity in organics, that they typically absorb in the UV region on us. We learned that in our first instrumentation class, and if you've not taken the instrumentation class before, then this might be the first time that you're hearing it. So this is what happens. Maybe if you took the instrumentation class, you still don't know it. So maybe this just saying it again kind of says, oh, that's why we did that back in the day. So something like benzene is colorless, but we can put benzene in a UV vis instrument, measure it in the UV range, and it will absorb UV radiation. And it's all due to the aromaticity and the conjugated double bond systems that are in those molecules. So all of these bases, A, T, G, and C, and U, have these aromatic rings associated with them. And these rings can measure absorbance in the UV portion. The UV nanometer range that we typically scan is going to be about 260 nanometers. You know, 254 is always kind of the area that we go to when we know that there's an aromatic ring involved. And depending on what other groups are on there, that 254 can slightly shift back and forth. And this is really close to 254. I mean, it's not a carbon ring. There's nitrogens involved in the ring. So, of course, it's going to be slightly offset. There's also functional groups on these rings, so of course that's going to offset it again. So it's not going to be perfect every single time. So 260 is typically the measurement that we make when we concern ourselves with DNA analysis using a UV vis instrument. So this is a UV portion, and UV basically means a quartz cuvette. I don't want to use plastic because plastic is not going to do me any good in UV. I also do not want to use glass. Glass Well, that's typically done invisible, and it's typically done in organic solvents. That's why you don't use plastic, because organics would eat the plastic. But with the UV portions, we typically have quartz cuvettes every single time. So quartz cuvette, turn on your UV vis instrument, go to a fixed wavelength of 260, and then you can start measuring these samples with that. Okay, so what contributes to the 260? I mean, why is this so important? Well, what you'll see is that the DNA will come to us in the form of two strands in the beginning. So here's a strand and here's a strand, and these bases are basically hooked up together in the middle. And when we heat these things up, what you see is a separation of the two strands. And then we will see one strand that will come off with some base pairs, and then we'll see another strand that will come off with some base pairs. And now these base pairs in the center, they are more exposed. They're not in the middle of the actual DNA at all anymore, right? These two strands have been separated. The base pairs are now more exposed than what they were, and because they're more exposed, they're actually more exposed to the energy associated with the UV radiation coming from our instrument. So they absorb more, and we see a higher absorbance reading because of that. So at a certain point, what will happen is that in these UV vis DNA analysis is that you often see DNA, double-stranded DNA, have an absorbance value. So absorbance value is going to be over here on the y-axis. It will have an absorbance value pretty much constant as long as the two strands are basically glued together. And then at a certain temperature, as I begin to heat this thing up, at a certain temperature, these strands separate from each other. And when the strands separate from each other, it opens up my nitrogenous bases for UV radiation more. And when that begins to happen, because I have these molecules now that absorb light, well, my absorbance skyrockets. And then there's going to be a certain point where it doesn't increase anymore because my strands are already separated out, and we see it kind of flatline off again. Very similar to a titration curve, almost identical shape. Over here on the x-axis, this is going to be temperature. So what we're doing is that we're taking a double-stranded DNA, and we're heating it up slowly, and we're measuring the absorbance as we heat it up. And then after a certain temperature, which looks to be about right here, after a certain temperature, the absorbance is going to skyrocket on us. And the reason for that, again, is because these bases are now more exposed to the UV light. So they are absorbing more. So the absorbance skyrockets from that point. And then once everything separates, once all of my bases are kind of exposed and absorbs the light that they absorb, you typically see that absorbance flatline and come back to a constant number. So titration curve, very similar. This thing basically is a titration curve in the making. This temperature at which this happens is called T sub m, and that is called the melting temperature. So in regards, we kind of look at this as the temperature at which the DNA melts, but it's not really melting, it's really disassociating, but we call it the melting temperature anyway. So this is what we do as far as DNA studies go. We heat it up, we can put it into a UV vis instrument, we can measure it at 260, and then we can look at that absorbance and figure out maybe some concentration levels of the DNA molecule itself. And that's what you're going to see on the next portion of the slide. When DNA denatures, the absorbance values typically go up by 40%. We call this the hyperchromic effect. So on a test, if you're asked to describe the hyperchromic effect, that is basically what you need to say. It's where the absorbance of DNA skyrockets because now these two strands are more exposed to the UV radiation. The shift, like we said before, is monitored at 260 nanometers, and that's due because these bases are now more exposed in the instrument. So here's a graph in your PowerPoint, and this concerns the melting temperature of DNA. So this is the melting curve that we just really got finished drawing on a sheet of paper. And what you're seeing is just like I told you here in the beginning, you see a flat line basically when it concerns the absorbance at 260 nanometers. Notice this is above zero point 0.5, which is good. Our working range for a UV vis instrument is anywhere between 0.2 to zero point 0.8. 1 is okay, but anything after 1.5 is really too high for any instrument. So what we're seeing here is an absorbance from DNA as a whole, and then here at the melting temperature, it looks like in the 80s, right? Here's 80 and here's 85, so it looks kind of like in between, 83 or somewhere on this chart. This is the melting temperature, and this is really the equivalence point, if you want to think of it that way, of a titration curve. So at this point, at this temperature, we find a spike in the absorbance. It goes to 0.75, and that absorbance continues to go up as these base pairs are getting more and more pronounced, and it reaches the equivalence of a 1 absorbance up here at the very top, and then it begins to kind of flatline and level out. So that's what we call the DNA melting curve, or T sub m, which is called the melting temperature, and that is why we see that kind of phenomena happen with the UV vis instrument. It's simply due to the fact that as you heat the DNA strand up, it is separating, these bases are becoming more exposed, and they absorb more light from the instrument. So it's a very good way to measure concentration. It's a very good way to see if your DNA has actually been separated at that point, and we can use UV in order to accomplish that. So that's what you're seeing here as far as the melting temperature goes. Please note that more hydrogen bonds means harder to separate. So the GC base pairs are actually harder to separate than the AT base pairs. And the reason for that is the GC base pairs have 3 hydrogen bonds that are the glue that holds those base pairs together. Now that's also dependent on a couple of other things in the solution, and one of them is pH as well. So not only the GC pairs determine the melting temperature, but the pH of the solution determines the melting temperature as well. Are we in an acidic solution? Are we in a basic solution? If so, we can get this DNA to unravel a little bit easier, a little bit harder. The concentration of the solvent that we put it in also has an effect on how well these strands separate, and the nature of the solvent as well also has an effect. So am I putting it in an aqueous solvent? Am I putting it in an organic solvent? What am I doing with it? So all 4 of those components go and contribute to the melting temperature of DNA. So that's probably going to be a test question, right? Give me 3 or give me at least 2 factors that contribute to the melting temperature of DNA, and you're seeing the number of GC base pairs, the pH of the solvent, the concentration of the solvent, and the nature of the solvent. All 4 of those are very, very important. Okay, so in the next video, we're going to turn toward the next portion of the DNA theory, and this is going to be translation. So how does it do what it needs to do? I want to kind of put your focus, though, on the semi-conservatism as far as DNA replication goes. This was proven by using heavy hydrogen, called the Mesolin-Stahl experiment. And basically what went on is that they put heavy hydrogen into the DNA, and they kept track of of where the heavy hydrogen showed up, or nitrogen showed up, and in what proportions did it show up into. So here we get a mixture of different nitrogens as far as isotopes go, and they begin to spin it down into test tubes looking at densities because they are heavier, and the heavier it was, the more nitrogen 15 that it had. And what they saw is that over a course of time they began to lose some of the heavy nitrogen content, and this is really what proved the semi-conservatism of DNA.